All right, let's do this. So, so what happened? So my wife was playing a video put out just recently by Paul Beckwith. We listen to him quite a bit. He does a lot of presentations, discussions on his YouTube channel about climate change and the science of climate change. He talks about the IPCC reports and other scientific papers, presentations, things like that. That's fine. He keeps things fairly current, and he keeps pretty much on topic, so that's good. He's a good resource, Paul Beckwith, on YouTube. So for the second time in the in a month, he's brought up some discussion about what happened in Antarctica this year, 2023. Um, Antarctica is in the southern hemisphere, so our winter is their summer. Um, Last summer, their summer, they had a melt event that was off the charts. So a lot of this is hard for people to understand. My wife and I talk about this all the time. She's really smart. She's not a scientist, but that doesn't matter. She's still a very smart person, and smart people can sometimes even have trouble with this because this all of these events are operating outside of human uh, experience. People don't experience science directly. We experience it through instrumentation, and it takes a certain amount of training, really, to understand instruments, how they work, what they measure, and what the data means. There's statistical analysis, there's charting, um, and for some types of science, including what's happening with the Earth dynamic system, you also need training and understanding of system dynamics. Okay, system dynamics. Again, I can even say that, and most people who would hear someone talk about system dynamics wouldn't have any idea what they mean. And that's yes, exactly. That's my point. That is my exact point. Is that nobody understands system dynamics. Now, everybody has had a little bit of experience with system dynamics, and the things that are happening, uh, they don't know that. And the things that are happening in Antarctica should not come as a surprise. In fact, with what little exposure most people have had to discussions of system behaviors, the events in Antarctica that just happened recently ought to be extremely alarming. And I'm going to get to what happened in Antarctica. I don't really have to because I had a video previously about this. Um, uh, there was an aspect of it that Paul Beckwith was talking about that I think illustrates why we have so much trouble with this. And that's why I'm doing this video. I'm doing kind of a meta analysis. I'm analyzing what he thought was the problem with this set of observations. And I'm going to critique his analysis of this set of observations. And I'm critiquing the analysis of most, probably virtually all people who are looking at this problem of global heating, climate change, and system change, because very few people think in terms of whole system dynamics. I've been in science for a long time. I I have a master's degree in biology. I understand science very well. I understand the history of science. I understand scientists. I've been around a lot of scientists. I understand what they do. I understand their motivations. Science is a career path for a lot of people, and a career path requires you to take certain steps to advance your career, to become an expert in your field, to become respected. And the commercialization of science, when it didn't used to be commercial, right? Science used to be a hobby for rich people, mostly rich white people. So that has changed. Now it's a commercial operation, and talking about science, doing science, has now been subsumed into consumer culture and capitalism. So, not for me. I'm one of those old school philosopher scientists, and um, that's kind of what I'm bringing to this discussion. I don't expect Paul to do that. I don't expect my man to do that. I don't expect Peter Carter to do that. I don't expect even James Hansen to do that. Everybody is doing science, science nouveau mechanism, which is commercial science, science in service of capitalism, essentially. So I'm gonna get to what kind of triggered me in a moment. But first, I want to discuss why this is really important, and I can bring people into this discussion in a way that most can actually understand immediately. And I want to do that first. And what I want to do is I want to tie what's happening in the Antarctica uh, with this major event that took place recently that has people completely unhinged. They're just completely running around with their hair on fire. Okay. I want to tie that to something that most people already understand, which is this thing called the butterfly effect. The butterfly effect and chaos. Chaos. Now, chaos culturally has a negative connotation. We don't want it in our lives. We avoid it. We run away from chaotic situations. We have police and armies and diplomats and laws and all these things to try to forestall or quell chaos. There is a cultural attitude about chaos that it is a negative, always. That being the case, there are chaos agents, people or countries or organizations, corporations that feed on chaos, that leverage it and use chaos towards specific goals. And there's a tension culturally between running from chaos and other people pursuing chaos. That's why chaos never leaves the world. That's not the chaos I'm really talking about here. I'm talking about formalized numerical statistical chaos. There is a field of study called chaos theory. One of the things that came out of chaos theory, it's been romanticized a little bit. Chaos theory is actually very, very simple. And I caught this way early on in my own career because I'm a systems analyst and a whole system theorist. Okay. I understood chaos theory right from the get-go. And it apart from the romanticization of chaos theory that you'll get out of books or YouTube channels or things like that, there is an actual science of chaos study. And one of the things that we learned by studying chaotic systems or chaotic machines, chaotic mechanisms, one of the things we learned is that a feature of chaos, which has been summarized and celebrated in the so-called butterfly effect. An element of chaotic systems is that they can and frequently do evidence, meaning you record, you see, there is evidence of stability in chaotic systems that make them look like they're not chaotic at all. And this is why it's such a fascinating field to study. They have this property that chaotic systems are really only identified and understood in hindsight after a period of stability vanishes. And it doesn't vanish in a predictable way. Lots of systems will evidence stability and then start to decline, right? Agricultural practices will work for a long time and then they'll start to not work anymore. People won't understand why it's not working. Well, maybe it's salinity in the soil. Maybe it's a new pest has arrived and is living in the soil or on the plants. You can't see it. So something about your agricultural practices is no longer optimal. Okay, that's because many biological systems, or certainly species assemblages, do not evidence chaotic behavior. They are self-righting. They are self-leveling. They are self-controlling. And this is actually one of the principal and key definitions of life is that it is self-righting. If it gets disturbed, it comes back. If it gets disturbed, it comes back. It tends to want this even keel And when biological systems in particular are disturbed, flung this way or flung that way, there are internal mechanisms that we observe that tend to bring them back to the middle. So chaotic systems were kind of not even identified for a long time, this numerical chaos, okay? And when they were identified as a mathematical observation that the behavior of these systems, they are not self-regulating, that they fail catastrophically, that when this was understood and that things did not tend to be normalized all the time, that there are systems that evidence a type of behavior and then fail catastrophically, this became intriguing. Um, a good example of a chaotic system is, and people can observe this, so it's a good place to go. Sitting, you're at a ski resort and you're sitting in the lodge, and it's snowing. You're not going to go skiing. You're sitting in lodge. The lifts aren't going. It's considered too dangerous to be on the mountain, and you're reading a book, and the snow is falling, and the snow is falling, and it falls for an hour, and it falls for another hour, and it falls for another hour, and in the back of your mind, well, there's snow accumulating on the mountain. It's going to be great skiing. At some point, they're going to open up the lift. So I'm going to be right on the lift. I got my skis right here. I got my hot cocoa right there. I got my lift ticket in my hand. I can't wait to get on the slopes and go skiing. You're watching the snow come down. It's beautiful. It's silent. It's quiet. No one's out there. And as you're reading your book, you look up, and the whole mountain comes down. Now we call that an avalanche. The whole mountain comes down, and you're in the lodge, and you might not even be in a safe place. If that's enough snow and it's close enough and it's heading in the right direction, that could go right through the resort, right over the lodge, blow all the windows out, flatten the place. Okay. It's an absolute catastrophe. Rock falls can tend to be the same way. People hike on the mountains, they climb the mountains, they do all these things. And for hundreds of years, it's been stable. Nothing happens. There's this rock. It looks kind of funny. It looks like it could fall, but it never has. And we just walk on this trail. And all of a sudden, one day, there's a bunch of people on the trail and the rock comes down. What happened? Something happened. Well, it was always ready to go. The snow was accumulating on the mountain. It could go anytime. One snowflake more, and it comes down. Okay. No one knows which snowflake that is. It could be now, it could be tomorrow. But the point is, it is the avalanche doesn't come down slowly, one snowflake at a time, the way it was built up. It builds and it builds and it builds and it builds, and nothing happens, nothing happens, nothing happens, nothing happens, and then it all comes down. These are chaotic systems. This has been immortalized as the butterfly effect. It's not really the best analogy. The butterfly effect is that small perturbations in initial conditions can give rise to vastly different behaviors down the road. It's why pendulum systems can be chaotic. You can hold a three-body pendulum at a certain point and drop it, and you can come back and do that and drop it from exactly the same point every single time. And tiny little variations in the behavior of that will cause that pendulum to swing in a very, very different chaotic way. Maybe it won't be at first, but eventually it will be. After a few swings, it's completely random. Okay, it's completely different. And no matter how many times you drop that pendulum from exactly the same spot, you think it's the same spot, it will behave differently. And these are mathematically, mechanically, in the case of a pendulum, chaotic systems. That's just inherent. You think you've got a handle on things. You think it's swinging the same way as it did the last 32 times you did this, but it's not. And in a moment, it's going to become absolutely chaotic. Three-body problems, currently, the three-body problem has no solution. The three-body problem has no solution because it is inherently chaotic. Earth dynamic systems, whether you're looking at biological systems or species assemblages, wind patterns, weather. Okay. A lot of these dynamic systems that make up the Earth, and there's probably thousands of them. I could rattle off a few, but it's not worth doing. There's 1,000 systems that make up the Earth, and they're all running at the same time. They're all, not all, but many of them are geared together. So you got this system that's pretty much its own thing. Maybe it's ocean currents. You have this other system, pretty much its own thing, whale populations, and yet they're geared, okay, because the ocean currents influence food supply for the whale population, okay? So, but the ocean currents don't move the whales around, and the whales flipping their flukes don't move the ocean currents around. They're not obviously connected, but they are geared together. And so the Earth system, which you think you can see from space, but you can't. You can't see it from space. You can't see it from the beach. You can't see it from a mountaintop. You can't see it from an airplane. You can't see it standing on the ground. You can't see it flying over in a balloon. You can't see the Earth system, but it's there. It's there. It's made up of all these subsystems. Some of them are geared together. Some of them are geared loosely, like like you know ocean currents and wind patterns. Some of them are loosely geared. Some of them are strongly geared, like ocean currents and the movements of icebergs floating in the ocean. No surprise, okay, that they are geared together. But you can't see any of this. You can't see any of this. There's no way, no place you can go where you can see any of this. And scientists like to pretend, and I'm using this word deliberately. I'm one of those, I'm a scientist, okay? And I'm talking for my community, and I'm saying this deliberately. Scientists like to pretend, I've already discussed their motives. Scientists like to pretend they've got a handle on things. They don't. They don't. I'm not sure they ever could. Chaotic systems like the three-body problem are inherently uncalculable. You can't calculate them. Now, maybe there's some supercomputer in the future that can solve every three-body problem for every possible input. Okay, well, that's one three-body problem you solved. What about all the others? And what about all the other chaotic systems that make up the Earth dynamic system? You're going to study all those now? You're going to have a supercomputer for every one of those? I don't think so. It is theoretically solvable, but as a practical matter, the Earth system, which contains many of these chaotic elements that appear stable until they break, okay? They appear stable until they break. It's a lie that they're stable. It's an observation of stability that is not true. The system could be inherently chaotic, and we simply haven't watched it long enough. Okay? So, no one's believing these lies on purpose. We're trying to wrap ourselves around a system that we are embedded in that influences us economically, in terms of our food supply, in terms of our weather, in terms of where we can find habitat, in terms of species extinction, in terms of everything else. We are embedded in it and it affects us. It is bigger than us. We are smaller than it. We are inside of it. It is outside of us. It is our everything. We have a vested interest in understanding the everything, but we can't. I don't think we can based on current technology, but also if it is truly a chaotic system, then we can't fundamentally, we cannot understand it. Now, there's a lot of climate science, and this has been my problem with climate science and the discussion of climate science, that has emphasized a predictable linear behavior that, okay, it's hard to move these things. So we're just going to project the current behavior out into time forever, literally forever. We're going to pretend that nothing changes. Then we're going to look at it and say, well, what if we did change something? Then what it'll do? Well, then this other thing will go down. And since it's geared to something else, that other thing that's geared to will go up. And maybe, but it'll all be linear. Well, we're just going to draw a line. And it's going to draw a line that goes out forever at a slightly different angle. And some lines go out and they're flat. They never change. Some lines go out all forever, but they go down in a linear way, a straight line. You could draw a line with a ruler. Just draw a line down. Some of them go up Okay, you just draw a line with a ruler, and it's predictable. Okay, that's some of that is just human bias. That's how we think things are. We watch our children grow up; they get a little bit bigger every year, but they do have growth spurts. I wonder what that's about. Oh, just ignore that. Children grow up. That's all we have to care about. Uh, People driving up and down the street. There's lines on the street, and they stay between the lines, and they stop at the stop sign, and everyone starts to stop at the same time. And when the light turns green, everyone goes at the same time. It's all highly regulated. All this engineering, everything is very predictable. It's very regular. It's going to be the same tomorrow as it was today. Um, that's a bias. That's a bias. It's a normalcy bias. Everyone carries that around in their head. It has to do with how we relate to each other, where our food supply is, how we're going to hunt, how we're going to eat, how we're going to reproduce. Everything is predictable. There's all these patterns. You draw inside the lines, you drive inside the lines, you obey the laws. The laws are there for a reason. We're trying to defeat chaos, and everything's going to be predictable, and it's a human bias. We build predictable systems, we enforce them with laws and engineering, and then we expect everything to be that way. That there's nothing in our daily lives to prepare us for collapse. Now, if you're a historian or an analyst of history, then you have been prepared a little bit for this idea of sudden collapse. Now, again, our normalcy bias, we don't actually study collapse. We don't have college degrees in collapsology. We don't have a curriculum in high school and junior high about collapse studies. Okay. We don't have news channels that have a segment right after sports on collapse. Okay. What's collapsing today? Today in collapse. You could go from today in sports to today in collapse, and we could prepare ourselves mentally for it, but we don't because of our bias. And scientists are doing this too. The scientists that are studying the Earth dynamic system have a bias. The denialists will tell you that their bias is alarmism, and they just want to scare us and make us stop driving our cars, and their bias, they're all leftists and communists, and they're trying to destroy America. That's what the denialists will tell you. Well, I'm here to tell you that there absolutely is a bias. It's not a conspiracy. No one got together in smoke-filled room and said, here's our bias today. Everybody has it. Everybody who's gone through an educational system and who didn't actually set out to study collapse, they have this. They just have this bias, and there's no attempt anywhere in our civilization to nullify that, or at least address that. So climate scientists have been watching the Antarctic, and they've been seeing that the ice was pretty stable. Now, in the north, at the Arctic, there's been a very different observation. And that's not too surprising, actually, because the ice in the north sits on water. So it is heavily influenced by conditions in the sea. The seas are undergoing rapid, amazingly difficult changes right now. So the ice that's sitting on the sea in the north is going to be heavily impacted by that. Right now, the seas are as hot as they've ever been, and this is going to have a heavy impact through melt on the ice in the north. So we kind of are not too surprised. The changes in the north are happening the way they are, and that they can be related directly to the sea. But the ice in the Antarctica is based largely on land. It's a continent. It's not even an island. It's a continent. It's huge. It's as big as Australia. And the ice on the land is not as much influenced by conditions in the sea. Also, there are differences in circulation patterns and heating patterns at the north end of the planet as opposed to the south. There's more land in the north than there is in the south. There's more water in the south than there is in the north. So there are already changes in between the North and South Pole that have to do with geography. So we're not too surprised that things in Antarctica have been different. And what we've been observing in Antarctica, to the delight of the denial people, is that the ice, by and large, hasn't been melting. It's rather consistent, and there's no trend. If there's a melt year, well, then the next year there might actually be more, and it just seems to be bouncing around in a kind of a natural, noisy way around a certain expectation. So here we go. We have this expectation that in the Antarctica, that the level of ice, the behavior of the ice is like this predictable thing. It isn't actually flat. It goes up and it goes down. That's a seasonal thing. But if you factor out seasonal variation, then the behavior of the ice is predictable. Within the seasonal variation, it's actually predictable. We can predict what's going to be 2 years from now, 5 years from now, 8 years from now, and we expect it to be like right here. Okay, except that in 2023, rather abruptly, no one saw this coming. No one knows what happened. Uh, no one knows if it's going to continue. No one knows if it's going to revert itself. Uh, there was a massive collapse. Now, remember, the bias is, oh, well, it's just going to kind of do this thing. Factoring out seasonal variations, predictable seasonal variations, it's just going to do this thing that it always does. And the bias has been established even through all this global heating that has really affected the North Pole ice. And we have that observation. And the fact that the Antarctic continent and the ice on the Antarctic is really stable suggests that, oh, well, now we know something about the Earth dynamic system. We know that the ice in the north is more affected by global heating than the ice in the south. And that's just a fact. There you go. We got a fact, people. Let's just write a paper on that and I'll publish this and I'll get citations and I'll get a Nobel Peace Prize, whatever. Okay. It just is not affected as much by global heating. And the deniosphere comes trotting out and say, ha ha ha. If global heating was a thing, then the Antarctica would be melting, and it's not. So global heating is a hoax. So there, quod erat demonstratum. And okay, well, you can't really say that because we don't understand how any of this stuff works. We're just observing whether it's trending one way or another way, or if it's just being stable and not really having a trend. But that doesn't work. That is not how this thing works. It has the appearance of normalcy, the appearance of predictability, has as much to do with the size of this machine as anything we know about it. It's just so big, and there is so much ice, and things happen slowly on human timescales that we feel like we can predict what it's going to do. It's like an ocean liner. You know you can't stop an ocean liner. You know you can't turn an ocean liner in less than 10 miles or whatever the figure is for a particular ship. And so that's just predictable. We know it's heavy, it's big, it's moving at a certain speed. It's going to continue to do that. If you want to stop it or turn it, well, you got to do a lot of work. And so it's going to take a lot of work for all this global heating stuff to move the system. And when I first learned about global heating and the CO2 effect, the greenhouse effect relating to that, the estimates were, oh yeah, in 300 years, maybe we'll see some changes that really show up in the instrumentation. We'll see some measurements and maybe say, yeah, it is getting warmer. Oh, there is a little more sea level rise. Look, the ice is melting. That's interesting. Well, yeah, it probably should be melting because global heating, but we didn't think it was going to happen right away. That's this normalcy bias. And you can actually, you can calculate how quickly ice should melt. This is physics. It is not a big deal. How much ice is there? Okay, that's a number. How thick is the ice? How wide? How big? What's the distribution? Okay, now I have how much ice do I have? What is the temperature of the ice? Is it right at freezing? 32 degrees Fahrenheit, or is it way below freezing? Okay, now I have that number. And what's going to melt it? Well, the sea is going to melt it. So, okay, fine. What's the temperature of the sea? Well, the sea is warmer than the ice, or the sea would be ice. So it can melt the ice. But look, the sea is really cold. So we know the difference in the temperature between the ice and the sea is going to warm the ice and cause the ice to melt. I'm doing all this, right? All right. This is how they do it. It's a spreadsheet. And there's all these calculations that people have calculated, and you run it through the spreadsheet and you get, oh yeah, it's going to take this ice sheet 300 years to melt. You could do the same thing with an ice cube that you put in a soft drink, right? You say, okay, how's long it's going to take this ice to melt? You drop this ice in, And you could sit there and you could time it with a watch and you could watch it. You could also do a calculation. You could say this much ice, this much water, this much of a temperature difference. When I drop the ice in, according to my calculations, it will take 8.5 minutes. That you could time it, verify your the correctness, and half minutes or so later, it's gone. Okay, it's math. It's just math. We understand this pretty well. We can do the experiments in your home. How quickly does ice melt? Okay, scale that up to an ice sheet. And they were looking at the Antarctica, and they were looking at all the ice sheets around the Antarctica that had exposure to the sea, which is not a lot because a lot of the ice is land based. But at the edges, there are places where the ice on the land flows into the sea and then floats out on the water. Ice floats out on the water, forming what's called an ice shelf because it's like a bookshelf in your house. It's supported on one end, but not the other. So it's an ice shelf. It's floating out over the water. And they calculated that, oh, yeah, sure, these ice shelves could melt. They could melt. It's going to take a long time. They're big, they're thick. The water is not that warm. And so it's going to take a long time. But yeah, sure, global heating, that ice will melt. And the Larsen A ice sheet, after people said, "Oh yeah, well we'll watch Larsen A ice sheet." It's the northernmost. It's in the warmest water. Not that you'd ever want to be in that water. Probably kill you in 5 minutes. But it's warmer than some places else, and so we'll watch the Larsen A ice sheet and see how long it takes for it to melt. The Larsen A ice sheet disappeared overnight. Disappeared overnight. Now, from that, you might say, "Oh, well, their math was wrong. They didn't understand ice melt at all." No, they understood ice melt perfectly well. It didn't melt. It collapsed catastrophically. It vanished. It broke into pieces and floated away, and it wasn't there anymore. Now, the ice is somewhere, it's melting, but for all I know, it's out there still in the ocean melting to this day. But the point is, it's not where it was. It is gone. And I remember when that happened, people lost their fucking mind. Not because the Larsen A ice sheet was so important, had economic purposes or whatever. There weren't even any penguins living on it. Okay. It was 100 feet out of the water. It was so big. It was useless to anybody. They didn't freak out because it was so valuable and now it's gone and boo hoo. They freaked out because what it told them was they did not understand that system. They didn't understand it. So for a bunch of scientists who walk all over the Larsen A ice sheet and drill holes and sample the ice and take measurements of the wind and temperature of the water and the temperature of the ice and do all this stuff, whole careers built on studying ice shelves. And that one included. Papers written, talks given, people teaching classes, talking to their students. Yes, I spent an entire summer on the Larsen A ice sheet, and well, I can tell you it's huge, and it's important to know how big these things are. Next year it was gone. Next year it was fucking gone. Okay, and people in my area of work, science, lost their cotton picking minds, lost their minds. It was something to behold. Now, why did they lose their minds over the collapse of the Larsen A ice sheet? Because it attacked their system of normalcy bias, that it's going to disappear through melt. That's how the ice in my soda disappears. It melts. It doesn't jump out of the water and run across the room. It disappeared in the soda because it melted, because the soda is not frozen. And the ice is warmed by the warm soda and it melts. So when Larsen A collapsed, people who weren't even studying the ice sheets, people who simply were scientists who thought they had a handle on how this Earth system works, lost their cotton picking minds, lost their minds. It was the biggest shock that the system of Western science had received probably since Darwin. I've never seen anything like it. People talked about that for 6 months. And of course, what they were talking about wasn't, oh, we've lost the Larsen A ice sheet. What will we do without it? No, what they were talking about was, how did we get this so wrong? How did we? How what did we overlook? What did we not understand? We clearly didn't understand something. We thought it would take this thing 300 years to melt, and it's gone overnight. I mean, literally, someone was looking at it through satellite photos, and they went back the next day to look at it on the satellite photo, and it was gone. Where is it? How did this happen? Where did it go? It's not there. Now, Larsen A wasn't the only ice sheet. It's called Larsen A because there's a Larsen B. Oh, and while we're on the topic, there's a Larsen C. Not anymore. There isn't. How did they get that so completely wrong? We have equations for ice melt. The problem was it was a chaotic system. There was things going on. We didn't see them. We didn't understand them because we don't understand chaotic systems. There was something going on with that ice sheet that we couldn't see, and we thought we knew, and we didn't. We just didn't. And it broke. It just broke. And it's like the avalanche. You think you understand what's happening on the mountain. Oh, the mountain's getting a lot of fresh, powdery snow. I can't wait. Got my lift ticket, got my skis. As soon as they start those ski lifts, I'm out there. I'm on that. I'm on that mountain. I feel like I've got a handle on this. Down comes the mountain, kills everyone, takes out the ski lifts, goes over the lodge, blasts out the windows. How did we overlook that? How could that have happened without us understanding that? Because it never happened before. We have this normalcy bias. And one year after another, it snows on the mountain, and the mountain accumulates snow, and then they start the ski lifts, and people ski, and they buy the lift ticket, and they buy the room in lodge, and they buy the skis, and they're buying the hot cocoa, and they're having a great party, and there's all these beautiful rooms. And one day the mountain comes down and wipes it all out because you didn't understand the behavior of the mountain. That's a rare event. It has an element of chaotic behavior. Nobody knew that there was going to be a snowflake, or of dropping pine cones, something up there on that mountain happened. And that whole thing came down catastrophically. It didn't melt. It didn't all come down one snowflake at a time like it built. It didn't come down in little waves and little fun little waves that you could ski on as they come down like surfing or something. It broke loose and it came down, and it was a billion tons of ice, and it wiped everything out. And that's what happened on Larsen A and B and C. I think C, maybe there might be some part of C left, but that's what happened. Now, current events. Something broke in Antarctica. The amount of ice around Antarctica has catastrophically failed. Catastrophically failed. The last 10 or 20 years of, the ice isn't melting. The last 10, 20 years of that narrative just fell apart catastrophically. It was going along, and then bam, it's gone. Why? It's not quite gone, but there was a huge melt. Nothing, and then a melt event. Now, that's not quite the same as a mountain coming down and snow avalanche. It's not like the ice went away. It's not like Larsen A, where the ice literally vanished. Goodbye, sayonara, see you never, okay? But the events observed in Antarctica are having an impact on the scientific community, the same as the collapse of the Larsen ice sheets did in their time. People who thought they had a handle on things. Oh, the ice around Antarctica, well, it's mostly land-based ice. It's protected from the water. The water is getting warmer, but it's not that much warmer. The winds are changing, but they're not changing that much. So, there's a lot of ice. The ice dominates. The ice is dominating all these other things, and the ice is protected. We don't expect a lot of melt. It doesn't mean that climate change is a hoax. It just means that it's a different situation down at the South Pole than the North Pole. And then boom, not true, but just not true. You didn't get it. It. You didn't get it. What is it? It's not that you're a bad scientist or that your equations are wrong or you don't understand ice melt. We understand all these things. We have equations. We got satellites. We got spreadsheets. We got supercomputers. We have got a lot of knowledge. We study this stuff. We talk to each other all the time. The it that you didn't get was that the system had inherent, now we see, the system had inherent chaotic elements. It is a chaotic system. The Earth dynamic system is going to turn out one of these days, someone's going to get the Nobel Prize for stating the obvious, which is that the Earth, taken in its totality, is a chaotic system. We had no business pretending we understood what it was doing. We had no business, in particular, conducting large scale, global sized experiments on a system that not only did we not even partially understand, but it turns out who knew had chaotic behaviors. Who knew? You shouldn't be messing around with chaotic systems, let me tell you, because they can collapse. In fact, that is what they do. They do not behave in a linear fashion. They are very unpredictable. They go along, they'll fool you. They'll go along looking like, yeah, I'm not a chaotic system. I'm not a chaotic system. You can predict me. You can trust me. Okay. And then, gone, broken, up here. What happened? It's gone. It melted. It drifted away. They're all dead. Whatever it is. And that is the nature of this problem. That is why these discussions on global heating and climate change and biodiversity and the sixth mass extinction drives me crazy. Drives me nuts. I get 5 minutes into these discussions. I say, no, that is not how it works. That is not how it is. You're assuming that, you're pretending that, you think you got a handle on things. Your career has prepared you for this system to be predictable. Everything you've studied, everything you've seen on TV, everything you knew, every conversation you ever had, every job you ever held, every relationship you were ever in, every time you went skiing has prepared you to accept that these things are predictable. These things are not predictable. All these things are inherently chaotic. They are chaotic systems. They are prone to sudden collapse. That's the reality. Now, it's very difficult to study these things, and it's very difficult to get a grant to study chaotic systems. In fact, the thing we've learned about chaotic systems is you don't study them. You don't study them. You observe them. Well, that was pretty messed up. Look at that. Well, why did it do that? Well, we'll never know why it did that, will we? Because it's a chaotic system. Yeah, there you go. And how are you going to get a grant? How are you going to get a PhD? How are you going to get tenure at a university to study a system that can't be studied? Because it is inherently chaotic. You can observe it, you can wait for it to do something strange, but you can't study it. It can't be predicted, and it's not self-sustaining, and it will not endure. Chaotic systems that are in the process of being deflected will go somewhere. They will go somewhere, and you're probably not going to be ready for it. You're not going to be ready. It's going to happen. It's going to happen to you, and you're going to be sitting there flat-footed or knocked on your butt. You're going to be standing there or sitting on your butt, gobsmacked what this thing just did. These systems are chaotic. They are inherently unstable. They will not stay where they are. They are on the move. All of them are on the move. There's thousands of parts of the Earth dynamic systems. There are thousands of gears in motion. They are geared to each other heavily, lightly, barely at all, strongly. They're all in motion, and this whole system is moving. It is going somewhere. It's going somewhere, and the surprises and the shocks and the dismay are going to come one after the other as these gears fall out of this machine, as they reverse direction, as they lose their gearing, as they gear to something else completely different, unexpectedly. We are in for a series of increasing with frequency and increasing disastrous surprises. We are entering an era of consequences. I can see it. I can see it falling apart already. This system is on the move. We've done it. We broke something. And we're going to keep breaking things because we don't understand. We're chimps. We're like chimpanzees. We're just tearing out the wiring and tearing out the gears and throwing things in random directions and banging on this and putting a stick in that. We don't even know what we're doing. We're just chimps. We're stupid. We don't understand. The system is bigger than us. We're embedded in it. We are a tiny part of it, and it is huge. And we have kicked it. Finally, all of our finger poking and thumb poking and sticking and stabbing and grabbing and pulling, we finally did it. We finally did it. Yay, us. Aren't we important? Aren't we critical? Aren't we clever? Well, this was our ark. This was our home. This was our habitat. We fucked it up. It's on the move and it's going someplace. And I don't know. And I don't know that it's taking us with it. Now, Guy McPherson, another commentator on this, 10 years ago, he was making predictions, now somewhat discredited, but just wait, okay? Now somewhat discredited, but just wait. He was making claims. I can follow his logic. His logic wasn't bad, okay? That when the Arctic, the northern pole, melted, the lack of reflective material, ice, would cause a sudden and catastrophic heating of the North Pole. So if we ever had a relatively complete ice melt, probably in the summer in the north, right? That the amount of solar input would push the system beyond a breaking point. So that's like the one snowflake on the mountain that brings down the mountain, okay? That there would be a melt event that would allow just enough solar energy in, which we don't know how much energy that would be. We don't have a number for that. But his theory was not a bad theory, that the north would heat up enough suddenly, randomly, unexpectedly, that the ice would just vanish catastrophically. And then that becomes a feedback loop. If the ice is good at insulating the surface of the water from heating because it's reflective, you think, oh, ice cools things. No, it doesn't. The ice itself does not, but by reflecting solar energy, it can maintain the ice. The ice itself doesn't do that, but the reflective nature of the ice is a feedback, an aggravating feedback for ice formation. So that if the ice suddenly vanished, both on land and at sea, because of a warming event, that the aggravating feedback of ice creating ice would vanish, and that instead the system would flip over. So this is the avalanche. This is the catastrophic breakup. Okay, this is the catastrophe that no one can see and can only recognize in hindsight because it's a chaotic system, right? He was predicting that it's a chaotic system, and there are many of them. So this is not fallacious. That it is a chaotic system, and once there is enough ice melt and therefore heating, we will reach a critical heat melt point where the system can no longer freeze. It can no longer freeze because the ice, unknown to us, the ice was actually critical to the freezing of the north. Now the north has no ice. The north was where the heat was going to vanish, to disappear. All the global heating goes to the poles, melts the ice, and is gone. It just did work. The ice is now in the ocean. That's sea level rise, but that's a different problem. So the heating is going to the north, melting the ice, and there's no heating anymore. There's melted ice, which is a different set of problems, but at least there's no heat. So the ice was providing a service. The ice also determines our climate in the mid latitudes. So like the US, Europe, parts of Russia, Asia, the mid latitudes, their weather is determined by the presence of ice up in the north. So his theory was that when the ice collapsed, vanished, that because of the lack of aggravating feedback, there would be no ice. So now we have a multi-year problem. The ice collapses, there's no ice, therefore there cannot be ice because ice makes ice. Now there cannot be ice. It is warm, it is water and land, and it's warming under the influence of the sun, and this changes weather patterns. The weather patterns are changing catastrophically, very suddenly, and all the things that you thought were normal and eternal, like rain in the winter and the sun in the summer, and the temperature is going to be this much in the summer and this much in the winter, and it just always goes between those two. And once in a while it's a little warmer, but it comes right back. A couple of days, it's right back where it's supposed to be. All that predictability, all that bias, all that normalcy bias, everything goes out the window. Goes out the window. People wouldn't even know what hit them. People wouldn't even know that the Arctic has suffered a catastrophic ice loss. They wouldn't even know. Wouldn't even be in the news. People who study the cryosphere would know that. People who could see the satellite images would know that. They'd say, "Where'd the ice go?" It would be like the Larsenet ice shelf. One day it's there, next day it's gone. Where'd it go? I don't know. I thought you had it. No, I'm not. I wasn't dealing with it. That's your job. Well, it's gone now, so we don't even know where it went. Okay, that kind of thing. One day it's there, next day it's gone. Literally, could even be a week. Okay, everything looked fine, and then it was fucked. Guy McPherson's thesis, and at some point, I think it becomes a little unhinged, but it's never wrong. Okay, it's never wrong. These are just probabilities and number games. So let's just go forward with this. His thesis was that the sudden and catastrophic, okay, change in weather patterns would influence where we could grow food catastrophically. Again, this word is going to keep showing up because it's all cascading. It's one avalanche causing another avalanche, causing a third avalanche, and it's just avalanches all the way down. It looks like one big avalanche to you if you're at the end of it, but to system scientists, it's one thing causing another, and it's all catastrophic. It's all been set up. All the dominoes were set up in a certain way, and the first one falls, and then the second one, and this will proceed catastrophically, quickly, like an avalanche, like the breakup of Larsenet. It will proceed catastrophically. That's a prediction. We won't know until it happens. But the understanding, the systems approach, understanding to these things, that they are chaotic in nature. They have chaotic elements. There's a particular bias about that, but that doesn't mean it's true. And if the Larsenet ice sheet could disappear, and if Guy McPherson is right, and the disappearance of ice in the north is going to have catastrophic and cascading ill effects, then the ultimately, uh, what happens to human civilization? If the place we located our cities, and the place where we grow our food, and the places where humans are, our habitat, is all dependent on all these system parts geared together in a particular way, and now it's all going to collapse catastrophically, or a big part of it will, then it could be that the growing zones that worked for thousands of years don't work anymore. It could be that the places where we put our major cities that was okay for thousands of years isn't okay anymore. One There's a movie, a piece of fiction called Day After Tomorrow. It's about a catastrophic collapse in the Earth dynamic system that results in the onset of a global ice age, not global, but certainly in the north, ice age in the north. Not even ice age. I mean, who knows how long it's going to last, but the movie calls it an ice age because they're just trying to use terms that people are familiar with. Now, there are problems with the science, and people gleefully point out the problems with the science. Um, I like the movie. I've watched it a bunch of times. It's not really about this. The science isn't bad, by the way. The science is not bad. Uh, what the movie does is it discusses not so much the science as how people interact with science and how people interact with calamities. And in the movie, a small change in a part of the dynamic system leads to a cascade of catastrophic failures in the Earth dynamic system. Interesting. That's interesting to me. That is how it actually works. So that you can have cascading catastrophic failures that you couldn't predict because they're chaotic, that you can only understand in hindsight because that's how chaotic systems work, like the avalanche, the last snowflake. Which snowflake was it? What was its serial number? Okay, we'd like for it to be that way, but it's not. We just have to monitor these systems and watch when they fail and try afterwards to do a postmortem of forensics. Why did it fail that way? Maybe we shouldn't have ski lifts here. Maybe we shouldn't have a lodge here because that mountain can do that. Now we know that. Now we know that mountain can do that, does this when there's that right snowflake, okay? And that mountain can do that, and maybe it'll do that in the future, probably. So maybe we should not have a ski lodge here. See, we do this after the fact, forensics. And in the movie, they're doing forensics. They're watching this thing happen. They weren't predicting it. They weren't ready for it. Everything was going to be groovy. Nothing was going to happen. Everything was great. New York was in the right place. Chicago was in the right place. The ships on the sea were doing the right thing. Everybody was where they were supposed to be. And then suddenly everyone died. Suddenly everyone died. And, people will say, that's not realistic. Well, maybe not that exact scenario, but the scenario that a small perturbation, a snowflake, causes a catastrophic collapse. That scenario is realistic. That is the behavior of chaotic systems. They are non-linear. They can even look linear. They can look linear for a long time. The Larsen ice sheet did not collapse year after year after year. It was always there. People studied the Larsen ice sheet. They had satellite photographs, and they probably had people walking around on top of the ice sheet and measuring the ice and the temperature of the water and measuring the temperature of the ice. And they're doing all this stuff and say, well, this will be here for thousands of years. Let's go to another ice sheet, see what it's doing. Then one day it was gone. That actually happens. That really happened. And when it happened, scientists lost their fucking minds. Not because the ice sheet was so important, but because it told us we're wrong. We're wrong. We walked all over that thing. How could we have missed the fact that it was going to go? We were wrong. And what was wrong is not that science is stupid or it's immoral or it's unethical. What was wrong is people have a bias and they don't understand chaotic systems. And Antarctica is a chaotic system. The Northern Polar Sea, the Arctic Ocean, is a chaotic system. It just is. The entire Earth dynamic system is created out of hundreds, if not thousands, of chaotic systems geared together. And the only reason it seems normal is because it hasn't been disturbed. And it just goes along doing its thing. So what disturbed the Larsen A ice shelf? Why did it vanish overnight? Literally overnight. Why did something that should have taken hundreds of years to melt vanish overnight? Well, now you see. Now you do have some science to do. Oh, yes. In this case, it's called forensics. It's forensic analysis. What happened? Okay. The avalanche happens on the mountains, comes down, takes out the ski lifts, takes out the lodge, kills hundreds of people. A week later, after they've rescued everybody and gotten all the bodies out and did all this, cleared the roads, then the forensic engineers come in. What the hell happened here? It's always after the fact. Chaotic systems cannot be studied. They cannot be predicted. You don't know. You're pretending to know. Good for you. You don't. You just don't know. Admit it to yourself. And what they don't admit is that these are chaotic systems. That they have elements of chaos. The chaos is embedded. It's there. It's a 3-body problem, if it's not a 5-body problem, okay? That these systems are highly chaotic. It is built in. The fact that they appear to behave predictably does not make them non-chaotic. And the avalanche on the mountain proved that that was something that had a chaotic element. It just took one more snowflake and that whole thing came down. So I started this by talking about Paul Beckwith, and he was analyzing this data about this terrible thing that's happening in Antarctica, which is the loss of sea ice. And it's not that the sea ice, and he went on to mention, and I'm not critiquing Paul, okay? I'm just saying why I'm sitting here, okay? He did fine. He does fine. He does an okay job. but he's not a system scientist. Okay. So and hardly any of them are. So he and all the rest are doing the best they can with a set of biases that these systems are predictable. And he was pointing out that people are really concerned that there was this massive deviation in ice extent in Antarctica that no one can explain. Well, it's due to global heating. Well, maybe it's due to El Nino. Okay, they're proposing reasons why it happened, but they don't know. And what needs to be discussed is in all of these things and all of our prognostication about the Earth system and how it's going to behave under global heating, what we always have to admit is and understand tacitly from the beginning is that these are chaotic systems and are inherently unpredictable. They are unpredictable. You can try, but there are elements in these systems that are unpredictable. The Larsen A ice sheet did not take 300 years to melt. It collapsed catastrophically. And then the Larsen B right next to it collapsed catastrophically. And then the Larsen C right next to that one collapsed catastrophically. We're being fed some information here. We're being warned. We're being told you don't know what you're talking about. And it's not because you're stupid or because you're immoral or because you're corrupt. You don't know what you're talking about because you don't understand what you're talking about. The system is bigger than you. You are embedded in it. You do not have a bird's eye view. You have an ant's eye view, and you are stuck here. And you have worse still, you have a normalcy bias. So when people are talking about, oh, wow, Antarctica, ice collapse, and the ice is gone. We don't know why. And here's going to be the impact of the ice. It's going to impact the penguins. It's going to impact shipping. It's going to impact sea level. It's going to impact forcing variables in the Antarctic area. It's going to force. It's going to change sea currents and salinity levels and the winds, and everything's going to change because there's so little ice. That's not actually the problem. The lack of ice in Antarctica is a problem, but that's not the problem. The problem is we didn't understand. We were taken by surprise. That is the narrative. We don't know what's going on down there. My narrative is it is a chaotic system. You will never know. You can't predict it. It's going to do things that are going to surprise you. It's already doing things that are going to surprise you. Larsen A surprised a lot of people. A lot of people lost their mind about that. And when Larsen B went and Larsen C went, they were like, okay, let's try to get our heads wrapped around this real quick. And when they talk about the Thwaites Glacier, also part of Antarctica, being the Doomsday Glacier, this is scientists waking up to the fact that they're missing something. They've been missing something. And if the Thwaites Glacier goes, if the Pine Island Glacier goes, then it's going to be hell to pay. Hell to pay. It's going to be bad. Larsen C didn't really do anything. It just shocked the hell out of people. And the current melting regime in Antarctica doesn't really make a big difference, but it shocks the hell out of people. What just happened? What just happened? We're doing forensics now. What just happened? Wait, back up. What? You did that? How did it do that? What do you mean you don't know how it did that? Someone should know how this happened. What's our model? What's our prediction? Could it ever do this? No. Well, it just did this. Why? How? When? We don't get it. Running around, hair on fire. Get some people down there. Do some forensics. We got to get our heads wrapped around this. This should not happen. It did happen. It happened catastrophically. It happened unpredictably. Why? Why? Well, of course, that's the problem. We don't know why, because it's unpredictable. It has elements of chaotic behavior. Okay, that's your narrative now. That the Earth dynamic system, as evidenced in the North Pole and the South Pole, just to start with, but also the heating of the ocean. People weren't ready for that. Why are the oceans at record temperatures? We don't know. We didn't predict that. Oops. I wonder how that happened. Well, now we're doing forensics. What happened? People are doing it right now. As I sit here on this camera, people are doing forensics right now on why the oceans get so fucking hot. Oh, and by the way, that's not going away. And the Larsen A ice sheet isn't coming back. And probably, the ice that just melted around Antarctica is also not coming back. But in any case, we don't know why it's not coming back because we don't know why it went away in the first place. Oh, well, it went away because of global heating. No, it didn't. It could have done that any time in the last 20 years. It didn't. Now it just did. Why? Well, it's because of El Nino. We've had lots of El Ninos, and we've had lots of El Ninos that were worse than this one. And we've had El Ninos during increases in global temperature. So why is it all of a sudden now? You're going to say it's global heating, it's El Nino, it's something else. I don't think you know. That's my point. I don't think you understand this system at all. I think you were looking in some other direction. And while you were doing that, something else over here was happening. Some other gear turned, and it turned this gear, and now the ice is gone. An unpredictable part of the ice is gone. Anyway, so that's why I'm here. I think we just need to admit that we don't understand these systems. And just possibly, if they are chaotic or largely chaotic in nature, if they have chaotic elements, then the point is we cannot understand these systems. And if that's true, then all of our predictions that we've got 20 years to go net neutral and net zero, and we've got 50 years before we have to worry about sea level rise, and we've got 100 years. No, you don't. You do not have any of those things. You might wish you had those things. It might be nice if you had those things. It could be great if we had that much time. But I'm looking at a chaotic system that's flying to pieces. Flying to pieces in unpredictable ways. It is a chaotic system. It is unpredictable, inherently unpredictable. And it is flying to pieces in ways you could not predict because you can't. And if that's the case, if we are embedded in this machine that is rapidly disassembling itself and is doing so in a way that cannot be predicted because it is inherently chaotic, then we should stop this experiment. We should stop. We should leave all fossil fuels in the ground because that's the perturbation that set this whole shit show off. Leave them in the ground now, immediately. Oh, well, that's going to have economic impacts. Let me tell you about economic impacts. Okay, 270 feet of 270 feet of sea level rise is going to impact the shit out of you. An extra 50 degrees Fahrenheit added to every continent in the summer is going to disturb the shit out of your economics. And any one of those things, including the sea level rise, sad to say, no one wants to predict that, but if there's a chaotic element in there, it could. We're already seeing this with temperature. Any one of these things can destroy human civilization. And it's not even the 270 feet of sea level rise. If something were to happen chaotically on the Antarctica that would, or Greenland, that released really unexpected amount of water, why would it do something unexpected? Because it's chaotic. It's going to do unexpected things all the goddamn time. That's what they do. And if it suddenly let all this water down, we might get a foot of sea level rise. We might get a foot of sea level rise in a few years. That's ridiculous. You can't say things like that on camera. Yes, I can. Oh, yes, I can. Yes, I can. I can say it because it is within the realms of the laws of physics. Well, that's some pretty extreme physics. Yeah, and they thought Larsen would never disappear. It disappeared overnight. That sounds pretty extreme, doesn't it? No, it means you don't understand the dynamics of that system. That's all it means. You just didn't understand. And I don't have to know in advance what's going to bring a foot of sea level rise from Antarctica or Greenland or something else completely unrelated to either two of those. I don't have to know. All I have to say is that the first foot of sea level rise, not the last foot at 270 feet, okay, but the first foot of sea level rise is going to end Western civilization. I can say that. My prediction is as good as anybody else's. And looking at how people handle stress and looking at what a little tiny bit of stress, a little tiny bit of global heating and climate change did to European and US politics. Tiny, 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 tiny. Something that's actually more measurable. We're done. It's just going to finish us. Our democracies will collapse. We'll become autocracies. Why? Because we're already doing that with a tiny little bit of change. And political change is also catastrophic. The Germans in 1933 didn't know they were going to be going to war with the entire planet and that their entire nation would be leveled 5 years later. Okay, they just didn't know that. Well, not 5 years, 12 years from 1933. The rise of Nazis in Germany, 1933, seemed pretty straightforward, just politics as usual. The guy has some ideas. Some people like his ideas, some people don't. 12 years later, Germany's flattened. Not two stones stacked on together. Okay. Politics will do that. Politics has inherently chaotic elements, and it's not the sea level rise from 269 to 270 that ends civilization. It's the sea level rise of 1 foot from where it is now, which is already elevated. Another foot, and we're done. We're done. I can make that prediction just as well as anybody else. History suggests I'm right. Doesn't take much. The political changes, the changes in attitudes, people's panic, selfishness, greed, all of it, it's all there. And we're working with a system that can easily, at this point, seems inevitable, will perturb us humans, chimps, in ways that seem small before they happen. But when they happen, it's like that snowflake that fell on that mountain that's had snow on it for thousands of years and never had a problem. Then that one extra snowflake brings down the whole mountain of snow. And it's like that. Humans are like that. So what's going to be the one little thing that pushes us over the edge? Is it going to be an extra 5 degrees Fahrenheit in the winter? Is it going to be an extra 1 inch of sea level rise? Is it going to be something else? And pretty soon, all the democracies in the West fail. They're all overwhelmed with totalitarian regimes and theocracies and millennial end times preaching. And who knows? It's a chaotic system. Can't predict it. And that's why I'm here. You don't know what's going on. You don't know where this is headed. This could be heading in a very, very bleak, bad place, and it could go there catastrophically. I will probably come back on here to discuss this again as it keeps recurring to me that people are missing the point. The point, we can get lost in the numbers. We can get lost in the math. The point is, what is being revealed to us is that we don't really know what's going on. And that's not a slam against science. That's not a slam against the work that scientists do. It's a slam against normalcy bias. You are working in an inherently chaotic system. You don't know it is a fact. You won't know it until something breaks. You're not going to talk about it in advance. And frankly, you have financial interests in just assuming that it's predictable. Because if it turns out that the system you're studying is unpredictable, then what's the point of studying it? And literally, that's it. You can't write a grant like that. You can't write a grant to study chaotic systems. They won't fund you because they don't know when you're going to get results or what the results are going to be or how useful the results are. It's chaotic. So why fund chaotic research? Not going to do it. And that's our blind spot. That's our blind spot right now. We're embedded in a system, an earth dynamic system that is complex beyond comprehension. And most, if not all, of that gearing has chaotic behaviors. Most, if not all of it, has chaotic behaviors. You want to be afraid of something? Yeah, there you go. You're embedded in this machine. And all the evidence is it's flying to pieces, and no one knows why it's doing that.